Bismillahirrahmanirrahim and Assalamu alaikum to you all. On behalf of DHA Education System, I welcome you all in my computer class. Course code is 2210. For week 2 of class C1, I'll carry out this session by taking the review of the topics covered in week 1, that was the binary systems and hexadecimal. Then I will discuss the topics and their learning objectives that we are going to cover in week 2. I'll explain the conversion methods and we'll take the quick recap of the topics covered. In the end, you people will be given the assignment to solve. Let's take the review of the topic covered in week 1. Number system. The system of counting and calculating is called number system. Categorically, there are 3 types of number system: denary number system or decimal number system, binary number system, and hexadecimal number system. The number system, which is based on 10 characters from 0 to 9, is called the denary number system or decimal number system. For example, if I say 75 with base 10, that is a denary number system. Similarly, 75.5 with base 10 is also a denary or decimal number system. So the denary numbers can be the positive numbers or can be the negative numbers. Denary numbers are used to represent various kinds of physical quantities. For example, time, for example, mass, for example, weight. So these are the different quantities that can be represented through the decimal or denary number system. Then comes to the binary number system. The number system, which is based on 2 characters, 0 and 1, is called the binary system. For example, if I say 1, 0, 0, 0, 0, 1, 1 with base 2, that is a binary number. Similarly, 110.11 with base 2 is a binary number. Binary number is the combination of zeros and ones. Binary numbers are used to represent electrical state of current or voltage that can be represented as on or off, as true or false. So on can be set as 1 and off can be set as 0. Hexadecimal number system. The number system, which is based on 16 characters from 0 to 9 and from A to F, is called hexadecimal number system. For example, 4FA with base 16 is a hexadecimal number system. Similarly, 5D with base 16 is also a hexadecimal number system. If I say 19 with base 16, that will also be a hexadecimal number system. Hexadecimal number systems are used to represent colors in HTML, are used to represent media access control address, that is a 48-bit binary address. So we use hexadecimal notation to represent the MAC address. This is also used to represent assembly language operation code. This is used to represent memory dump to find or to locate the errors and to debug those errors. In week 1, we discussed the memory units. Memory units are used to measure the logical size of the memory. The smallest memory unit is known as bit, which can either be 0 or 1. 4 bits makes 1 nibble. 8 consecutive bits makes 1 byte. 1 kilobyte is equivalent to 1024 bytes. 1 megabyte is equivalent to 1024 kilobyte. 1 gigabyte is equivalent to 1024 megabyte. 1 terabyte is equivalent to 1024 gigabyte. And 1 petabyte is equivalent to 1024 terabyte. We learned the conversion method from binary number to equivalent denary number. In that conversion, we use the binary notation. For example, the number is 1000111. We multiply each bit of this number with its equivalent binary notation. We add all the terms together to get the equivalent Denary number. There is a second shortcut method in which all the binary values are written. Then we write the binary notation and we add the number which are having the value 1. This is how we are going to get the equivalent Denary number. Then we also learned the conversion from a Denary number to the equivalent binary number. For example, if a number was given that was 120 with base 10. So we wrote all the binary notation and then put 1 under the notation which are required to find sum equals to the number that is given in the question and 0 in the remaining places. So all the on bits, their binary notations will be added together to get the equivalent sum to the number given in the question. So this is how a Denary number is converted into the equivalent binary number. There is another method to convert a Denary number into the equivalent binary number. That is known as the remainder method. In this method, we divide the number with the base 2 because we are going to convert the Denary number into the equivalent binary number. So we will be dividing the number with base 2 and we'll keep on dividing it. We'll write the quotient and the remainder in parallel, and in the end we will collect all the remainders from bottom to top, and this is how we are going to get the equivalent binary number. That was the topics we covered in week 1. Now let's see what we are going to cover in week 2. Topics we are going to cover in week 2 for class C1 are the numerical topics. Here you will be able to convert the hexadecimal numbers into the equivalent Denary number and Denary number into the equivalent hexadecimal number. By the end of this lesson, you will also be able to convert the positive hexadecimal integers to the equivalent binary number and the binary number to the equivalent hexadecimal conversion. In the end, you will be able to recognize the character set and the coding scheme used to represent the number system. Let's start the topic with conversion. Before starting the conversion from hexadecimal to binary and denary, we need to understand the relationship between hexadecimal, binary and denary. So a table is given here. This table is given in your book. Since 16 is equals to 2 raised to power 4, this means that 4 binary digits are equivalent to each hexadecimal digit. So table 1.2 summarizes the link between binary, hexadecimal and denary. So in the table, the very first column shows the binary values and the next column shows the equivalent hexadecimal values and the next column shows the equivalent denary values. We need to see how these values are formed. If you just look at the binary values, these are a group of 4 digits. You need to put binary notation on these digits, and that is 1, 2, 4, 8. So you will be putting the binary notation from the extreme right side of the given binary digit. So for example, if we have the number 1011, we'll be putting the binary notation on it 1, 2, 4, 8. And we'll add those binary notation which is having the value 1. So in this way, we have 8 plus 2 plus 1, which gives us the result 11. So if you look in the table 1.2 at the value 1011, there is an equivalent denary value which is 11. And 11 in hexadecimal is equivalent to B. This is how this table is formed. We will be using this table to convert a binary number into the equivalent hexadecimal number and a hexadecimal number into the equivalent binary number. So you can use this table as the reference. Binary to hexadecimal conversion. While converting from binary to hexadecimal is fairly easy process. Starting from the right and moving left, split the binary number into the group of 4 bits. Then if the last group has less than 4 bits, you can simply fill in with zeros from the left. That is not going to change the number but will complete the number. Take each group of 4 bits and convert it into the equivalent hexadecimal using the table 1.2 that we discussed in the previous slide. So here we are given with the 2 examples. Example number 1, in which the binary number is given. First, we will split up this number into the group of 4 bits and we'll start it from the extreme right side. So we have formed 3 groups here, and luckily all the groups are fully filled with the digit, so they are not less than 4 digits. So the very first one is 1011. If we put binary notation on this, 1, 2, 4, 8, and add the binary notation which is having the value 1, we get the equivalent hexadecimal number which is B. For the next group, the number is 1110. If we put the binary notation on this number 1, 2, 4, 8 and we add the binary notation whose value is 1, that gives us 8 plus 4 plus 2, which is 14, and in table 1.2 you can see 14 is equivalent to E, and the last group 0001, when we put the binary notation 1248 on this group, it is going to give us the value 1. So this is how we will simply convert a binary number into the equivalent hexadecimal number. For more clarity, let's solve another example. In this example, we are given a series of binary number. First, we will split up this number into the group of 4 bits. So we'll start from the extreme right side. We got 1, 2, 3, 4 groups. At the extreme left side, the last group is having 2 digits. So to complete this group, we will add 2 zeros in the start. Now we are going to give the binary notation 1248 on each of this group. And we'll be using the table 1.2, or we will be using the binary notation. If we do not want to use the table, we'll simply use binary notation. Otherwise, you can use the table 1.2, and from the table, you can find the equivalent values of hexadecimal. So 0010 will give you the value 2 from the table. 0001 will give you the value 1 from the table. 1111 will give you the value F from the table, and 1101 will give you the hexadecimal value D from the table. So this is how you can simply convert a binary number into the equivalent hexadecimal number. Now, if we are given a hexadecimal number and we are asked to convert it into the equivalent binary number, we will be using the same table or the same binary notation method. So the method is very straightforward. You will be using the table Simply take each of the hexadecimal digit and write down 4-bit code which corresponds to the digit. For example, we are given with the hexadecimal number 45A. Using table 1.2, you can find the equivalent 4-bit code for each digit. 4 is equivalent to 0, 1, 00. You can see that from the table. 5 is equivalent to 0, 1, 0, 1. And A is equivalent to 1, 0, 1, 0. We'll put the groups together to form one binary number. If you do not want to use the table 1.2, you can simply use the binary notation 1248. So you will be writing 1248, and to make 4, you will put 1 under the binary notation 4, and you will make rest of the binary notation 0. To get 5, you will put 1 under the binary notation 4 and under the binary notation 1, and you will put rest of the places 0. And to get A, which is equivalent to 10, you will be putting 1 under the binary notation 8 and under the binary notation 2, and rest of the binary notation will be considered as 0. So this is how you can get equivalent binary number. There is another example, BF08. Again, you can just use the table and simply from the table see the binary value of the B and write it down. See the binary value of the F, which is 1111. See the binary value of the 0, which is all zeros, and the binary value of the 8, which is 1000. Then put all the digits together, and this is how the hexadecimal number is converted into the equivalent binary number. To convert a hexadecimal number into the equivalent denary number is fairly straightforward. Take each hexadecimal digit and multiply it by its value. Add the totals together to obtain the denary value. Look at the following two examples to see how this works. For example, we are given with the hexadecimal number 45A. First, multiply each digit by its value. 4 will be multiplied with its hexadecimal notation, which is 256. 5 will be multiplied with its hexadecimal notation, which is 16. A is equivalent to 10, so 10 will be multiplied with 1. We'll multiply it all and then add the totals together, and we are getting the equivalent denary number this way. There is another example. We are given with the hexadecimal number C8F. First, multiply each digit by its value or by its hexadecimal notation. So 12 will be multiplied with 256. 12 is the value of C in hexadecimal table. Then the next digit 8 will be multiplied with 16, which is the hexadecimal notation. And then the last number F is multiplied with 1, which is the hexadecimal notation. Add the totals together, and this is how we get the equivalent denary number. Now I will explain the last conversion of this chapter, which is from denary number to equivalent hexadecimal number conversion. This method involves successive division by 16. The remainders are then read from bottom to top to give the hexadecimal values. For example, if we are given with a number 2044 and we are asked to convert it into the equivalent hexadecimal number, we will be using the remainder method. We will divide the number with 16. We'll keep on dividing it. We'll write the quotient and the remainder in parallel. And we'll divide it till we get the quotient lesser than the divisor. And in the end, we will collect all the remainders from bottom to top. So we got here 7, 13, 4 as remainder. 7 will be written as it is. 13 in hexadecimal is equivalent to D. So we'll write D instead of 13 and 4 will be written. So 2044 denary number is equivalent to 7D4 hexadecimal number. Before ending this lesson, we need to know a little about the character set. Text and numbers can be encoded in a computer as pattern of binary digits. Hexadecimal is a shortcut for representing binary. ASCII and Unicode are important character sets that are used as standard. ASCII stands for American Standard Code for Information Interchange. ASCII character set is a 7-bit set of codes that allow 128 different characters. 2 raised to power 7 makes 128. That is enough for every uppercase letter, for every lowercase letter, digit and punctuation mark that you can see on the keyboard. ASCII is only used for English language. If you just look at the table, here the characters are represented, their denary values are represented, their binary and hexadecimal values are represented in separate columns. So character A, which is uppercase character, is equivalent to the denary value 65. And then this 65 is converted into the binary value and used inside the computer. Similarly, if we have to use this capital letter A in hexadecimal addressing, the value 41 will be used inside the computer. Now, if we just look at the letter Z, which is equivalent to the 90, and it gives the equivalent hexadecimal number, which is 5A. Now there are a few other coding schemes that exist. For example, extended ASCII. Extended ASCII code is an 8-bit character set that represents 256 different characters, making it possible to use characters such as @ or C registered sign or copyright sign. Extended ASCII is useful for European languages. Then comes to the Unicode. Unicode uses between 8 and 32-bit per character. So it can represent any characters from languages from all around the world. It is commonly used across the internet. As it is larger than ASCII, it might take up more storage space when saving document. Global companies like Facebook and Google would not use the ASCII character set because their user communicates in many different languages. I will end up this lesson by giving a look on the ASCII table. This is a table. The first column represents the decimal number. The second column is the equivalent hexadecimal values. Third one showing the binary values. Fourth one is basically showing the symbols. These are the symbols that you can see on your keyboard. If we randomly look at the 32 decimal value 32, which is giving us the equivalent hexadecimal number 20 and is giving a binary number 001000000, And if you just look at the symbol, there is no symbol placed here, but 32 is a decimal value for the character space. Similarly, if you just look at the capital letter A, its decimal value is 65. And now if you just look at the lowercase letter a, its decimal value is 97. If you just look at the curly braces, the closing curly braces, its decimal value is 125. Here in the second diagram, you can see a URL, which is a website address, www.ruknuddin.com. So that can be represented in hexadecimal using ASCII code. If you just look at the table and find the equivalent hexadecimal numbers, you can see the arrows. W, if you just find lowercase letter w in hexadecimal number, the code is 77. So wherever you'll find W in the URL, you will straight away put 77. Here percentage sign is simply shown to make it a hexadecimal notation. And then dot, for the dot you will be writing the equivalent number, hexadecimal value is 2e, and then for small letter r it is 72, for small letter u it is 75, for k it is 68, for n it is 6e, for u it is 75, for d it is 84, for I it is 69, and again 6e, for dot again it will be 2e, for c it is equivalent to 63, for o it is equivalent to 6f, for m it is equivalent to 60. So this is how the URL can be represented into the equivalent hexadecimal notation using this ASCII code. That is end of this chapter. In this lesson, we learned the conversion of binary number to the equivalent hexadecimal number and the hexadecimal number into the equivalent binary number. We used the table 1.2 for that conversion, and we also used a binary notation method to convert the numbers from binary to hexadecimal and from hexadecimal to binary. Then to convert a hexadecimal number into the equivalent binary, into the equivalent denary number, we use the hexadecimal notation method, and to convert a denary number into the hexadecimal number, we used our remainder method. After that, we described the character set and three of the coding scheme: ASCII, extended ASCII, and Unicode. That was end of this lesson. Now there are a few practice questions given, activity 1.4, activity 1.5, in which you are asked to convert the binary number into the hexadecimal number and hexadecimal number into the equivalent binary. Activity number 1.6 and activity number 1.7 is given, in which you are asked to convert the hexadecimal numbers into the denary and the denary numbers into the hexadecimal numbers. So these are the practice questions. I hope you will practice it by using the slide, and you can take the help from your book. Thank you so very much for listening carefully.